Good morning. I'm pleased to present Team Phoenix Electric Corporation and our capstone project, the Fiber Optic Annunciator. Our two technical directors that assisted us on our project this year are Sandra Silva and Mike Smith, both of whom are URI alumni. My name is Eric Tatchery, and I'm an electrical engineer. My two colleagues are Brandon Bisgeyer, who is an electrical engineer, and Ayman Usmani, who is also an electrical engineer. Phoenix Electric Corporation, our sponsor for this project, is based out of Canton, Massachusetts, and focuses on the design and manufacturing of high-quality, long-lasting products for the power industry. First, we will start with background information. What actually is an annunciator? An annunciator is a system that monitors signals from a variety of locations throughout a building or an area and displays them in one location. Annunciators are commonly seen in the form of a fire panel. You may be familiar with the panels seen on the left, as these are usually located in the entrance of large buildings. Our annunciator will monitor the status of circuit breakers. Annunciators allow a technician to monitor the entire system or building from one place and be able to quickly check if everything is running properly or if there is a problem that needs to be addressed. The motivation for this project is to create a product that is not on the market yet. There is a market demand for electromagnetic immune systems that has not been met by any other products. There is an increased reliability when using this product due to not having the risk of false positives or false negatives due to electromagnetic interference. No other circuit breaker annunciators on the market use fiber optics to transmit the data. Our anticipated best outcome is to have a functional and working production prototype based off of the design that the 2019 to 2020 Team PEC created. Our design will be condensed into real-world form and be ready for full production by the end of the spring 2021 semester. Our annunciator will monitor the continuity of 12 signals coming from circuit breakers and then communicate the status of those breakers to the annunciator board. The display will then show the status of those signals with a green or a red LED. The main key accomplishments of this semester towards achieving our anticipated best outcome is completing the design of the input, annunciator, and display board, preparing the files to be sent out to manufacturers, and making significant progress in the VHDL code for the project. Since this product is a first of its kind, Phoenix Electric Corporation will be the company that customers will go to if they would like to have a fiber optic annunciator. The demand for this type of product will be redirected completely towards PEC. This annunciator will give the customer the most reliable and safest system possible. My contributions to this project were on the input side of PCB, as seen on the left side of our block diagram. The input PCB takes in 12 volts or higher and converts it to a usable 3.3 volts. This allows us to power our FPGA, which will monitor the continuity check signals that come from circuit breakers and transmit it through the fiber optic cable to the annunciator slide. Key items on the input PCB are the FPGA, which will be the brains of this board and monitors continuity check signals, the switches, which simulate circuit breakers, the terminal block, which will connect to the actual circuit breakers in the system, the fiber optic cage and connector, which will transmit our data to the annunciator board, the power conversion IC, which outputs 3.3 volts, and the Arduino Nano, which will assist us in debugging the board if necessary and gives a USB interface into the system. The biggest challenge in my contributions toward this project were related to the physical design of the board. The input board itself had over 20 feet of routes on a board that is 5.25 inches by 4.55 inches. The two connectors for our FPGA chip have 100 pins each, causing for very dense areas centered around the middle of the board. There are numerous new components on this design of the board that needed to be implemented correctly, including the power conversion IC, the Arduino board, a 50 MHz clock, and non-volatile memory. We also had to have placement of the FPGA connectors and the fiber optic transceiver connector perfect, as having it as little as half a millimeter off would result in a non-working board. This slide highlights the dramatic change between the 2019 to 2020 design and the new design we created this year. The old design required two PCBs connected by jumper cables and an extra FPGA on a breadboard to run the input side. This new design will compact all of that onto one PCB that only requires a power input. The switches that you see on the bottom half of our PCB are to simulate the circuit breaker continuity signal, so we do not need an entire circuit breaker system to test our project. The upcoming technical accomplishments for the spring 2021 semester largely depend on whether or not our custom PCBs are fully functional from the manufacturer. We will fully test all functionalities of the PCBs, including the features that the 2019 to 2020 team built and the ones that we built this year. If there are any flaws, we will focus on fixing them through either VHDL code or using our Arduino Nano if needed. If everything is functional, we will move on to finishing the VHDL code for the added features. Our final accomplishment will be creating a seamless GUI for the customer interface. This will allow our customers to create their system for their specific purposes. If the system needs to be changed or moved around, the customer will be able to plug into the Annunciator with a USB cable and have software that will allow them to change their inputs and outputs. This will prevent the customer from needing to edit the VHDL code and avoid possible errors in the code. Now, I would like to introduce your next presenter, Brandon Bisgeyer.
Hello everyone, my name is Brandon Bisgeyer, and I will be talking about some of the features of the Annunciator side of the design. The design of this board consists of an Annunciator PCB and a display PCB with LEDs. The fiber optic connection coming from the input board connects to the Annunciator board PCB. The Annunciator functions by collecting data that's being transmitted via the fiber optic cable and converting the signals back to digital to be displayed on the LEDs on the display board. The Annunciator is connected to the display board via a Molex connector to allow the LEDs to receive the incoming digital signals. The picture on the left shows last year's design for the Annunciator. The picture on the right is our improved design for the Annunciator board and display board. The key items on the Annunciator board include the following components. First, we have the FPGA connections to mount the FPGA onto the board, the Arduino Nano headers to be used for future debugging purposes, a Molex connector to connect the Annunciator to the display board, the fiber optic cage connectors to connect the fiber optic cable coming from the input board, and we have the 12 volt to 3.3 volt power converter, which converts the 12 volt input into 3.3 volts to be used throughout the board. The key items on the display board include the following components. First, we have the buzzer alarm that receives the incoming alarm signals, an identical Molex connector that connects to the Annunciator board, 12 LEDs that display the incoming digital signals, and 3 push buttons designated as Test, Acknowledge, and Reset. The biggest challenges for building these boards was definitely the routing. Since the board is so complex, switching to different layers for routing was a common task when building this board. Component placement was also a challenge because certain components could not be too close to each other so as to interfere with another connection. Requirements changes were also common since our TDs had new ideas or implementations they wanted to include onto the board each week. Design rule checks were also a challenge because via hole size and solder mask on certain components had to be correct according to the design rule check that we imported onto these boards. Some upcoming technical accomplishments for next semester include testing the Annunciator board in the lab to ensure full functionality once the boards are received by the team. Another task is to finish the VHDL coding for the alarm sequences to be programmed in the FPGA. We will also be submitting these boards for manufacturing and creating a bill of materials to be sent to our chosen vendor so that we can receive them before the beginning of the semester. Lastly, hand building the display board will also be another challenging task for the spring semester. Now, our next presenter, Ayman Usmani, will continue the presentation by talking about his technical accomplishments.
Hello everyone, my name is Ayman Usmani and I'm the third member of Team PEC. This semester, while my teammates worked on the schematics of our Annunciator, I have been using VHDL to design and implement new features to it. The first task I accomplished was to design an alarm system that fulfilled the requirements of the International Society of Automation, also known as the ISA. 4 alarm sequences were designed, each a little different from the other. Sequence A was the simplest, with an automatic reset. Sequence M was near identical, the only difference being a manual reset required at the end. The last 2 sequences, F1A and F3A, were both automatic resets with first outs and more alarm and acknowledge states. After the alarm sequences were fully functional and simulated, the next task was to design a preliminary version of the memory mapped I/O that will, in the future, be adapted depending on the requirement. The memory mapped I/O uses an 8-bit data bus to read and write addresses and data to 256 8-bit registers. Finally, an additional feature was added to allow us to manually switch processes so as to allow intra-FPGA reading and writing using the same 8-bit data bus. Thirdly, a finite state machine was designed that allows the user to manually select the severity of an alarm. The selection then sends the state machine into the allocated state, after which the length the horn stays on for is determined by a 10-bit counter that counts up to a higher value the more severe the alarm is. All horn settings were simulated and tested on the test bench and are fully functional. Lastly, the original input board VHDL files from previous year's PEC team were debugged after several failed attempts to implement them. The first step was to narrow the issue down to the timer or delay signal. Originally, the clock signal was suspected, but that proved to be functional in the test bench. Finally, it turned out that there was a mismatch in the size of the delay signal across the several source files, and so the input board was successfully implemented after that was fixed. As for my future technical accomplishments, I shall work on over the next semester towards achieving our anticipated best outcome, include continuing hardware testing to ensure the hardware that was set up last year continues to work as intended. Furthermore, I will also work on further additional features that will need to be added to the Annunciator through more VHDL coding. I will also assist in testing the previously built functions on the new custom PCBs that were designed by Eric and Brandon this semester. Lastly, I, along with the other 2 members of my team, will work on a graphical user interface to allow easy control and management of the Annunciator. Our Annunciator has made substantial progress thus far, but there's still quite a bit of work to get done. Additional features are to be added to the Annunciator based on the requirements. We are also yet to receive our custom boards from the manufacturer. Furthermore, we plan on manually building our design board and testing all previous functionalities from the 2019 to 2020 PEC team boards on the new PCB, as well as the newer ones we've designed. Finally, we also intend to add a graphical user interface to allow customers easy control of the Annunciator. Lastly, we would like to thank our technical directors, Mr. Sandro Silva and Mr. Mike Smith, without whom we would not have been able to achieve what we have so far. We thank Mr. Silva for sponsoring our project and for guiding us through the tasks that needed to be achieved. We also thank Mr. Smith for his invaluable technical support on our journey so far. We would also like to thank Dr. Sunak for helping us stay on track and for giving us the best capstone experience possible. Finally, we would like to thank all of you for watching our presentation, and we look forward to achieving our ABO next semester. Thank you.